You're listening to the Interactome, a podcast by a group of young researchers who want to connect you to the world of science by sharing their stories and perspectives. Just in case their bosses are listening, they want to remind you that the opinions expressed here are their own. They also want to remind you not to take anything they say as medical or professional advice, as they are not doctors. Not yet, anyway. Stay tuned about that. And, without further ado, welcome to the Interactome.
Hello everyone, and welcome back. It's Joe here, and I'm with my good friends Natalie and Sarah. We've been sharing a lot of interesting stories about many things in the life sciences, maybe a little bit of climate science in there too. But there's a lot of different kinds of science out in the world, and we want to make sure that we share that with you. And so here today we have one of our good friends. He is an astrophysicist. He is an astronomer. He is also, as he calls himself, a bona fide rocket surgeon. He is Kenneth Lin. Kenneth, thank you so much for being here. We're really excited to have you. And I guess starting off, how are you doing? And we're also just curious to hear a little bit more about you and the things you're doing.
Great. Thanks for having me on the show. Really happy to talk about what I do. Things have been busy, but we've been having a lot of fun with our new expensive toys that stare at outer space, and
Woo!
we've been learning a lot, and happy to share.
Yeah. So I guess just kind of starting off, what was your path like, kind of getting to where you are? Can you take us through your story a little bit? Maybe just kind of like how, like what got you into your field right now, and like where do you go to school? Things like that.
Yeah, so I grew up in a really small town in central Massachusetts, and I graduated in high school with a class of only 98 students. And it was great in the sense that it wasn't close to a city, so I was actually able to see the stars. But I've had a long-term interest in planetary science and in astronomy and physics. When I was really small, I really remember this book that I read where there was a personified cartoon version of Saturn, and it was floating in a bathtub. And I remember thinking to myself, how could it be that something so huge could be able to float in water? Of course, at the time, I didn't know anything about how density plays a role in this whole scheme of things. But later, as I progressed through high school physics and through college, where I majored in physics and astronomy, that I started to realize, wow, there are unifying physical principles behind these not only everyday observations of phenomenon that we see, but also in space and in the most extreme environments that we observe. So I went to college at the University of Massachusetts Amherst, and after I completed my physics and astronomy degree, I moved on to continue studying astrophysics at UC Berkeley, where I am now. And currently I work at Lawrence Berkeley National Laboratory, where I'm affiliated with both the Scientific Data Division and the Physics Division. So it's been a lot of fun working on these rather exotic problems for this many years, but it always amazes me that all of the findings that we're able to discover in these extreme circumstances of space also are the same rules that apply on Earth.
Yeah, super cool.
I'm going to jump in
Oh.
real quick with an honorary mention. I just want to say all the people on this podcast episode today were all UMass Amherst grads. I'm an aggressive UMass Amherst stan. I have it on my license plate and everything. So Really just needed to shout that
Wait.
out. We all graduated class of 2020.
Wait, Natalie, you are UMass?
Yeah, girl, it's on my car.
It's
I don't
on
know
your
what to tell
car.
you. It's on my car.
Oh man. All right.
Anyway, I totally digress this.
No.
Yeah.
No worries. Very important point. Very important point. But yeah, I guess kind of getting back into it. A lot of us as biologists, we kind of, the way we perceive like the problems that we're looking at, oftentimes like things are very complex. In terms of like one input may not necessarily have one output. Sometimes you can do one thing and like 50,000 different things happen in 50 different contexts, and it's all very complicated. And sometimes rules are a little confusing. And you just mentioned, Kenneth, that there are often some very interesting like rules and principles in physics. And I was just kind of curious to get your opinion on like how do physicists really see the world, and like how does that compare to something maybe like biology or ecology, and why is that important?
Yeah, that's an excellent question. So physicists and mathematicians, to certain extents, have fairly reductionist worldviews. So what I mean by that is the idea is to boil down complex phenomenon, complex interactions, and boil them down to their most simple form. And oftentimes when we go and observe certain phenomenon happening, our brains are not naturally used to or trained to understand the fundamental principles behind what we observe. So as a result, you'll see many things in nature that are counterintuitive, and that, oftentimes some things that you are not able to easily explain just by your intuition. And so physicists try to build this kind of intuition and try to counter your natural tendency to explain things in conventional ways that more likely than not will end up being incorrect. So one example is, does a feather or a rock fall down faster if you let both drop at the same time? And clearly on Earth, if you do this experiment, you'll see that the rock is going to land on the ground faster than the feather. But if you repeat the same experiment on the moon, where there is no air resistance or any other confounding factors that will interfere with motion, the feather and the rock end up landing on the ground at the same time. And this experiment was repeated by one of the Apollo astronauts back in the 70s. And so this is something that Isaac Newton predicted back in the 1600s and ended up being proven true hundreds of years later. And there are other examples too, which are a little more exotic, but there are things like superfluid helium, right? So if you take some helium, we know of it as the gas in balloons. It's a very light gas. It's actually very rare. It's very expensive these days. If you take helium and you cool it down to extremely low temperatures, and we're talking about maybe millikelvin above absolute zero, which is the lowest temperature that is possible, where atoms just simply stop moving. If we cool them to a fraction of 0K, you will find that helium becomes not just a fluid, not just a liquid, but it becomes something called a superfluid. And it has very interesting properties where if you have liquid helium in a superfluid state sitting inside a cup, it can actually creep outside the cup. It can climb the walls of the cup and creep outside. And
that's wild. Sorry, I didn't mean to interrupt, but that's so cool.
Yes, yeah, exactly. So superfluid helium.
Wait, sorry, I'm like a little confused. Through like osmosis, it goes through the glass.
It goes up the sides.
It
and
goes up
over.
the sides and over.
Oh,
So
oh,
the
oh.
superfluid
Okay.
helium is able to climb outside the cups. And the reason behind that is because in the superfluid state, there's zero what we call viscosity, or it's a form of friction. So there's basically it's a frictionless fluid. And so things like that are very, very unusual and counterintuitive to our brains. We're not really able to imagine it, or even try to fathom how this might work. But by studying physics, by reducing the complex to the simple, we're able to start to gain an intuition about what is going on, even if the results seem very unusual.
Thank you for that overview. You definitely painted a really good picture there. I always think that the comparison between the feather and the rock, it's just such a good example, because no matter how many times I think about it, I just cannot, like you said, wrap my brain around the fact that they're going to weigh this, or they're going to fall at the same rate on the moon. And even though you've said it and it's literally been proven true, it's hard for me to wrap my brain around it. So moving on to a little bit of kind of the physics that you do in particular. So you're an astrophysicist. Is that, I think, one big thing in science, or a common theme that people hear about, is precision and accuracy when you're doing scientific testing, or when you're in a lab setting trying to put together experimental conditions and answer a question. You can't put the universe into a lab. So how do you perform that research? And I mean, you talked about the man who went to the one of the Apollo missions, went to the moon. He tried that experiment himself. You can't go to the moon. UC Berkeley is not going to fund you for that. So wondering how that kind of looks. I know, wish they could, but they won't. So wondering what that kind of pans out like in your day-to-day as a physicist in the lab.
That's a really good question. And you have a really good point in that there are basically no possible means through which we're able to do tabletop testing of what we're studying. So, for example, we cannot measure the mass of the Earth, let alone the sun or the galaxy inside the lab. So that's obviously a big part of the challenge in the science that we do. We have to make use of limited information in order to try to extract as much out of that information as possible. And that is quite a difficult problem. One of the approaches that astrophysicists take is to prefer accuracy over precision. So in many other laboratory sciences, precision is something that is very important. You need to have many trailing digits after the decimal point. But because the scales that we're dealing with in astronomy are so vast, ranging from the size of the universe, which is the largest possible scale, to the smallest of scales at the atomic level, what we really want is an accurate ballpark estimate of values rather than a really precise number. So to give you an example, the sun weighs around 2 times 10 to the 33 grams. And it's not really that useful to talk about this mass with additional trailing digits. So, for example, there is no difference for us when we say something weighs 2.2 times 10 to the 33 grams versus 2.1 times 10 to the 33 grams. Versus just saying 2 times 10 to the 33 grams. Because at the end of the day, we're talking about numbers that are so large, 10 to the 33, which is a 1 followed by 33 zeros, essentially. That, at the end of the day, when we go down in place value, the significance of that diminishes significantly. So for us, it matters less that we have infinite precision, and matters more that we are able to get a ballpark estimate.
And Sarah and Joe, I mean, you guys both have experience in life sciences laboratories. So maybe what is the precision, or how does precision and accuracy play out differently in the life sciences, just so our listeners can kind of have a comparison?
Yeah, I think for me, a lot of times when I'm setting up my experiments, I need to be both precise and accurate in the sense that I need to be oftentimes, like, if I have a very, very, very small volume of liquid that I'm working with, I need to make sure any small volumes that I'm adding to that are like the exact, at least very, very, very close to the exact volume that I'm trying to put in, like the little test tube or things like that. And so I need to be both precise in terms of like as many, like in a lot of times, as many decimal places as I can after the zero, or after the decimal point. And I have to be accurate. I have to be close to that target value. And in a lot of cases, sometimes maybe we can sacrifice sacrifice precision a little bit as long as we're accurate. But I would argue that when you're doing something very, very sensitive, like when we're doing RNA sequencing, and we need like the same amount of RNA in every single sample, we need to be both precise and accurate. Whereas here, like, things are just so big that like in physics, correct me if I'm wrong, Kenneth, it seems like things are just so big that once you get to big, you're just really comparing different amounts of really big, in the sense that, like, yeah, the sun is big, but like 1.2 times the sun, as you were saying, like 1.2 times the mass of the sun isn't really that much different than 1 times the mass of the sun. But like a star that's like 10 times bigger than the mass of the sun, that's when you really start to see differences on the astronomical scale. If that,
right.
I don't know if I'm making sense.
Right. And I think there is one thing I might add is in astrophysics, because the length scales, the time scales, all of these scales have such a wide dynamical range. If we increase the precision, that is not telling us any more about the physics of what is underlying whatever that we're observing, than if we just truncate these digits to just an order of magnitude estimate. And by order of magnitude, what we typically mean is we're able to gain an accuracy of all values that we measure to about within a factor of 10.
Mm-hmm. I remember Kenneth and I, we've been good friends for a while, and he actually was offline. He was telling me about one of the classes that he's either running or thinking about running, kind of just like approximating interesting things. And I'm just curious if you could share with our listeners a little bit about that. I have some stories that I think we could share as well, but I know you have some cool points about like all the different things you can approximate using this kind of method,
right?
This kind of mindset.
Right. So one of the courses I'm teaching next semester is called Order of Magnitude Physics, and it's essentially a class that will train you on how to think not in a very precise way, but more of gaining an intuition of the physics in order to arrive at a relatively accurate answer. Because many of the questions that we pose, and sometimes people call them Fermi problems, many of these questions are either not well defined or are virtually impossible to answer in a precise way. So to give you an example, one of the problems may be like how much rubber is liberated by cars each year driving down a 2-mile stretch of Interstate 80 in Berkeley. And tires, they wear out over time, right? So you usually change your tire if you stick a penny in and you can see Abe Lincoln's head. So
I didn't know that. This is now a mechanics podcast. We're switching it up.
Yeah, so your tires will wear out after some time on the road, and obviously that will depend on how much you drive, and we're making some assumptions here. For example, you're not driving cross country every week. So based on these fairly reasonable assumptions, we should be able to arrive at an answer of how many kilograms of rubber is liberated just by this 2-mile stretch of highway in Berkeley. And this is something that you can go ahead and calculate. There are many steps that you need to take along the way. For example, you would need to try to estimate the size of an average tire, how much traffic passes through these sections during the day, how much traffic there is on the highway during rush hour, what the rubber release rate looks like if you have fairly average driving habits. And if you go through the numbers, you'll find with some deviation, you'll find within a typical 2-mile stretch of an interstate highway where you may have rush hour traffic in the mornings and in the evenings, that up to 20 to 30 tons of rubber is liberated per year just by tires. And where does the rubber go? It goes into the grass, it goes into the oceans, and it goes into your lungs. And so a lot of the problems that we think about have physics behind them. You just need to think about how the equations apply. And once you're able to solve these problems, they can have real world impact. And so these are the skills that we're trying to train.
It's really cool. It's interesting that you bring up the concept of thinking, because in this whole metacognition thing, because in the biological sciences, we don't really tend to do that as much. But in something like a physics, that's almost the entire discipline. And it's built off of, at least from what I've seen, these thought experiments. And I guess my question for you is, you also have a background in astronomy, which is a much macroscopic, it's much more macroscopic scale, whereas I guess astrophysics could also be macroscopic, but you're also looking at quantum scale and small interactions. So how have you sort of balanced those schools of thought in your mind as you've gone through your time? Because I think for me, I would definitely mix them up. How's been your journey with that? I know that's not an easy question.
Right. That's another good question. And you're right, it is challenging to bridge these two scales. In fact, one of the most pressing problems in physics is trying to bridge the quantum with the astronomical. The quantum world is often viewed as at odds with large scale physics, such as relativistic effects. And this is one of the major problems in modern physics. So many people are struggling with how you bridge these two scales. But at the end of the day, when we do physics and try to reduce everything down to its most basic form, one of the common questions that we ask ourselves is what effects dominate, when, where, and how. So at the quantum scales, at very, very small atomic scales, there are certain effects that dominate. For example, we may think about the strong and weak nuclear forces when we're thinking at the atomic scale. But we probably will not be worrying too much about gravitational effects, because gravity usually is something that affects large-scale structures. Whereas when we're talking about cosmological structure as a whole, what we care about are things like dark energy's gravitational effects, and we're not as worried about, say, electrostatics. So when we go between the smallest scales to the largest scales, we must ask ourselves which effects dominate and to what extent. And this is one way that we can simplify a lot of the very complex problems that we often face, and they're quite daunting. And we use, again, try to reduce things to their most basic form.
So with that in mind, having to go in almost like objectively to each question that you're faced with, maybe what are, it seems like you need to rewire your thinking to be a physicist. So maybe what are some things that come to mind when you think about thinking like a physicist? Like, what would you tell another person if they were like, how do I think like that? Or one of your students, perhaps.
Yeah, that's an excellent question. So I often say that physics is a way of thinking, and I didn't really fully appreciate that back in high school or even in college. But after getting more into the forefront of where the research is these days, I've come to realize that we really need to have a different sort of thinking in order to make any sort of progress. So there are a couple of things that physicists keep in mind when we do our work. So I would say the top thing is to always stay skeptical, and we never want to take claims at face value. And what this translates into is if someone gives you an equation on the street and tells you that this is what happens at the singularity of a black hole, you don't just take it as truth. You go and verify whether this equation is true by trying to rederive it or trying to compare it to the results that you might expect on first principles. So these things are all aspects that are critical if you want to make progress in physics. You need to always stay skeptical.
When you said you have to, you're not getting an equation on the street, I just thought of the old-timey newspaper people. Equation, get your equation here. And he's just handing it out on paper. That's what came to mind for me.
I got an image of someone walking up and being like, hey, I got some equations. No one's ever seen these before.
Exactly.
Give me $100 and I'll give you one of these.
Yeah, I mean, you never know. People publish a lot of papers, and oftentimes it is difficult to go and check someone's work. But nevertheless, it is crucially important that you go and rederive results and try to compare them to observations. Try to verify that there's some reality buried in the theoretical framework. So this is something that I would say every physicist has, is this real sense of being a skeptic of everything they see. And that is sort of a segue to the second aspect that I think is very important for physicists, which is to always be asking questions about anything, whether it be daily life or more profound questions about where we came from. And then the difference between a physicist and perhaps people from non-science backgrounds is physicists will actually go and try to answer these questions through experiment and observation. So ask questions and then actually go try and answer them. So this is something that is at the core of our work as physicists. And of course, in today's day and age, we're often told to sort of stay in your lane and not speak about something that is not within your formally trained zone of expertise. But the mindset of people who do physics is that we should always stay curious about everything, especially if it is not in our expertise, because we need to have a curiosity to learn something new and to question existing paradigms, because oftentimes we discover new and profound things when we step outside our field and are able to refresh what people had long thought to be true. So, the canonical example that people give is that Isaac Newton's kinematic equations were true universally, but in fact, they are just a specific case that applies on Earth and are generalizable through Einstein's equations. So you always need to stay curious and question the status quo, even if it's not within your expertise. It is okay and encouraged that you ask questions.
I love that.
Mm-hmm.
I definitely I think it's really important for all of us and definitely all our listeners to hear as well. I think a lot of I absolutely agree. This is something that physicists really, in my view, exemplify. I also think that these are really good principles for any kind of scientist to be the best kind of scientist that they can be. And so I really do think that Kenneth is, to all our listeners and everyone else chatting now, I definitely think that Kenneth is sharing some important principles that we can all take away from this. And maybe we don't necessarily have big fancy telescopes to observe the universe and things like that, which, I mean, I would love to have a big fancy telescope like that. But at the bare minimum, what I can do is I could think scientifically. I don't have to have a fancy lab to do that. And so maybe I'm trying to calculate, I don't know, how much air I'm breathing every day. You can find those numbers online and think about a few things to throw those together. Actually, Kenneth and I, a while back, I apologize for this, Kenneth, but we did a very, very important calculation. This is the power of scientific thinking right here. We calculated the amount of farts that our entire college campus may be releasing within a year. It was a large volume. We had to take into account the temperature, the average volume of CO2 at a certain amount of time, like papers that kind of talk about the volume of the average fart. These are very, very highly important things. And we didn't have a lab to do that. We just had our brains.
And to add to that, there are certain implications of flatulence on climate change, right? So this is actually significant output. We shouldn't be just blaming the cows, right?
So I'll just say, this is great. I love this story. The more that I think about physics and science in general and staying skeptical and staying curious is at the heart of all of science. And what Joe's basically getting at is just an innate creativity. I think if you can cultivate that curiosity and the creativity throughout your life, you're already doing science to a degree, right? It's all about making discoveries and innovating new methods and coming up with different ways of doing things. And actually, one of my mentors recently said some of the best creators and innovators are people who have the freshest eyes to something. because they're not so used to looking at things in the way that they've been taught necessarily, right? They're like not super into their discipline. So it's interesting you say all that, and it's definitely an attitude that I'm going to take forward, and I hope our listeners do as well.
Yeah, I mean, because astronomy is unique in the sense that we are often faced with problems that seem unanswerable. And so one of the first things we resort to is trying to ask questions and see what we're able to answer. And this attitude is what allows us to always be skeptical, because these are things that you can't just walk into a lab and test very easily. And so this builds a sense of healthy skepticism, I would add. And it actually is very encouraging when we actually are able to answer these questions, and it allows us to stay curious.
So I also kind of want to transition. We've talked a lot about astrophysics and physics in general, but I think I'd love to, and I imagine everyone on this call and our listeners would love to hear a little bit more about what you do, maybe in your day-to-day or what your research area is. So if you could kind of walk us through that, that would be great.
Yeah, so just to step back a little and familiarize everyone with our discipline, astrophysics is unique in that we have about 3 distinct focus areas that people usually work in. The first and most popular is observational astronomy. And this is essentially the prototypical astronomer, where they take a lot of imaging data, spectroscopic data from observatories, and then they go and analyze this data and try to discover something new, or try to go verify or disprove a theory, or go and do all sorts of different scientific what we call surveys. And so this is basically the majority of the astronomy community. But there are also 2 other major fields of astronomy. Yeah,
I have a quick question. What do you mean by survey? Like, when I think of survey, I think of like a form that people fill out, like, what's your opinion on XYZ, things like that. But I have a feeling that you mean something different. So I'm just curious about that.
Oh, right. So astronomical surveys are essentially catalogs that are millions of objects long. And in practice, what you do is you automate a telescope to scan the sky at some certain pace, at some certain rate, and you image these objects very systematically, and you basically are able to build a catalog of these objects and create an atlas of the sky. And so that is what a survey is. And many observational astronomers partake in these large-scale projects as part of large collaborations in order to accumulate as much data as possible in the most cost-efficient way possible from modern telescopes.
Cool.
Yeah, does that make sense?
Yeah, okay. Absolutely. Thank you.
So there are 2 other classes of astronomers. The second largest area is theoretical astrophysics. And essentially what theoretical astrophysicists do is theory. So they set out and try to explain the phenomenon that observers are picking up through their telescopes, and they try to interpret these findings and find the physical basis behind the phenomenon that we observe. So, for example, if an observer sees a very strong X-ray source coming from a nearby galaxy, that is not the Milky Way, then theorists may try to come up with an answer of where the source of this X-ray emission may be coming from. Could it be coming from a star exploding at the end of its life? Or could it be an accretion disk around the black hole that is actively eating away a stellar companion? We don't know, just based on observations necessarily. And oftentimes it comes to theoretical astrophysicists to help interpret some of these unique observations. And the smallest but likeliest, the most important, if I may say, class of astronomers are the instrumentalists, who include myself. Instrumentalists are quite a niche field, and what we do is improve the instrumentation, the detectors, the spectroscopes, the spectrographs, and all of these different parts of the telescope in order to push the limits of what we're even able to observe. So observers, of course, they make their observations, but it is the instrumentalists who are the enablers of new classes of observations. So in the past few years, we've seen a number of advancements in the technology of detectors and telescopes that have allowed us to make new classes of discoveries. So notable example is the gravitational wave observatories, the pair called LIGO. And LIGO first observed gravitational waves several years ago, and they continue to make these observations. But in the decades leading up to the first observation of gravitational waves, there was a lot of effort put in on designing and making instrumentation for these observatories, and also coordinating with optical observatories elsewhere on Earth in order to see any counterpart electromagnetic radiation emitted from gravitational wave sources. And so this coordination between new gravitational wave observatories and their instrumentation, along with precise detectors in optical observatories, have opened up a new field called multi-messenger astronomy, where we're able to observe both the electromagnetic counterpart signals of these so-called transient events with the gravitational wave signals that come from gravitational wave detectors such as LIGO. And this is a very important milestone because it allows us to actually observe and see with literally our eyes for the first time how the heaviest elements in the universe, such as gold, were created. Whereas before we had very little idea about how these heavier elements, rare earth elements, came from. From these technologies, we've been able to deduce that it is the collision of neutron stars and the explosion that occurs thereafter that creates many of these rare earth elements.
Wow. So if we want to do alchemy, we just take two neutron stars and smash them together and boom, gold.
Yes.
So easy. So easy to do.
So if Earth were near two colliding neutron stars, and neutron stars are very, very dense objects. They're almost entirely made of neutrons, and they're extremely dense to the point where a teaspoon of it would weigh of order Earth masses.
Wait, what?
How many?
A teaspoon of a neutron star material would weigh of order Earth masses. Not, a few kilograms, not a few grams, but literally a few Earth masses.
Wow.
Wow. So wait.
Oh, just a few.
Multiple
like,
Earths.
Just a couple Earths.
So I take my magical space spoon and I scoop up some neutron star, and it weighs like, let's say 4, 5, 6, maybe 10 times as much as the entire Earth.
So essentially that would be true. So a teaspoon of neutron star material, and if you want to put a number to it, it would weigh essentially 4 billion tons based on the density of the actual substance in neutron stars. And
That's
keep in mind
That's
that
a heavy breakfast.
these objects contain more material than the sun, despite neutron stars being only around 10 miles across, which is, to give you perspective, it's about the size of a city. Yet it contains more material than the sun. And so you do not want to be living alongside a neutron star, obviously. But if you were somehow far enough away from a neutron star collision, the amount of gold it would produce would be about, say, it could be about the mass of an Earth or the mass of a planet. You could have a planet of essentially gold. And so if you were in that situation, gold would no longer be valuable.
So what you're saying is I can't smash stars together to get rich quick.
Unfortunately, it would lose its value through inflation.
That's disappointing.
I have a question.
That's the next crypto.
I have a
Just meshing stars together.
I have a question. So, like, I know we're talking about smashing things together and, like, on the grand scale, maybe neutron stars, but, that's farther into the future. Right now, we're smashing different particles together, right? And where are those happening? Where, like, I can't just go to a museum and see, two atoms being collided, right? Like, where would the general public go to see that? Or could they even see that? Where are these laboratories?
Right. So, a lot of particle physicists with whom I collaborate a lot these days work at these large-scale particle physics laboratories, and they're often just rings buried underground, and they accelerate particles to extremely high energies and smash them with each other and see what comes out. And that is really really the central effort in high energy physics and in particle physics these days. So there are a few laboratories that do this. So the largest one and the most well-known, I think, is CERN, which is the Center for European Nuclear Research. And they smash particles together at very high at the highest energies of any particle accelerator on Earth. And they're trying to discover ultimately how subatomic particles behave, trying to characterize their masses, their spins, and other intrinsic properties of these particles that are very difficult to measure. And of course, one of the key drivers in modern physics right now is the search for dark matter and dark energy. So dark matter and dark energy are essentially complete unknowns for us, and we would like to find out what particles are responsible for comprising, or what particles are responsible for being dark matter. And physicists smash particles at higher and higher energies to discover if there is any sort of unknown particle that we have yet to observe.
So
how?
Oh, sorry.
A quick clarification question: like, how do we know that dark matter and dark energy exists? Like, it seems like we don't know what it is, yet we're talking about it. So I'm very curious, like, how do we like know that it's a thing, but not know what it is, if that makes sense?
Sure. So that's a good question. So I'll start with dark matter because we know a little bit more about dark matter. We know actually how dark matter behaves, and we actually know that to a fairly good precision. Ironically, we know more about dark matter and what it is not. Um, and we can do this through relatively precise measurements. And the reason we're able to do this is because we have yet to discover the nature of what these dark matter postulated particles are. So how did we find out about dark matter to begin with? So back in the day, many decades ago, there was a scientist named Vera Rubin, and she was making observations of galaxies, of specifically spiral galaxies. And spiral galaxies have arms, and you can see many of these pictures through public releases from NASA and other sources, and they're very photogenic objects that astronomers like to capture with their amateur telescopes in their backyards. Um, these spiral galaxies actually rotate, but their rotation is quite slow, at least on human timescales. Now, the sun actually orbits around our galaxy at around a velocity of 200 kilometers a second, and that sounds quite fast, but on the scale of galaxies, which are on kiloparsec scales, these are not fast at all compared to what we humans experience as time. So, how did we get to the point where we found out that there was dark matter? Well, Vera Rubin was measuring how fast stars were orbiting around the galaxy in these spiral arms, and she made these plots called rotation curves. And you would expect that when you go further out from the center of the galaxy, that your orbit rate is actually going to slow, or at least have some sort of decline because you're just farther away. But she actually found out that this was not the case, and that objects further away are orbiting basically in the same manner as objects that were closer into the center. And this is very unusual. It's yet another counterintuitive discovery. Why was that the case? Nobody knew. Was there hidden mass inside that we didn't know about? That is essentially how we came to the conclusion that there must be something called dark matter, because it is some sort of matter that seems to be there, but we cannot see it at all. So this is where the dark matter discovery arose. And so now we're trying to find what this matter could be. Is we're particle physicists want to find out if it is a particle, what kind of particle it is that would create this kind of large scale effect. Because if dark matter were as influential as it seems to be, then they should be everywhere. They should be passing through our bodies every second, undetected. So, these things likely don't interact very much with small scale things, but interact only at the larger scales. So this is one of the key open questions in modern physics today. Dark energy, on the other hand, is very different. It is not the same as dark matter. And to simply say it, astronomers and physicists have no idea what dark energy is. We have no inkling. And to this day, people are still trying to theorize what dark energy could be. How did we discover it? Well, in 2011, the Nobel Prize was awarded to a team, one of a team actually based out of Berkeley, where they discovered the accelerating expansion of the universe. And before that, the thought was, well, will the universe end by collapsing in on itself, or will it expand as Edwin Hubble found that it was expanding forever? It would just expand forever. But in fact, Saul Perlmutter and his team back in the 90s found out that the universe's expansion was not constant. It was not slowing because of gravity. In fact, it was speeding up as if there were some sort of anti-gravity energy that was being injected into the universe somehow. And the conclusion from that is that there must be some sort of extra energy, and people coined it dark energy.
Cool. Yeah. Wow. Wild. I'm super curious to see what unfolds in this whole field over the next decades, I'm sure. Kind of going back a little bit, I'm super curious, like, what your actual daily life is like. Like, so do you just kind of like get to the lab and like enter the magical physics lab and do magical physics things, or what does it actually look like to really do your research?
Right. So, as I mentioned before, I am part of the small niche of astrophysicists who focus on building new instruments and advancing the technology that goes behind these new instruments, such as new detectors and new spectrographs. And so I spend currently around a third of my time in the lab, and the rest of my time sitting in front of a computer doing software development and working on analysis of the data that we collect in the lab. And so in the lab, oftentimes we deal with things like cryogenics. So detectors usually have to be cooled to very low temperatures. And so oftentimes we use liquid nitrogen for that. And we do a lot of tests in the lab with the electronics. And we do in the computer in the office a lot of software development to operate these electronics and manipulate these devices and see how they respond and how they perform and how they would perform if used in a telescope. And so that is essentially the scope of our work. Some people may spend more time in the lab if they're doing a lot of hardware development, but oftentimes hardware requires some degree of software development as well. So it is important to have proficiency in both hardware and software aspects of your project. And one other thing that I think it is not just us instrumentalists that have to do this, but across all different scientific fields, of course, is a lot of writing, whether it be writing papers or writing funding proposals. And specifically for astronomers, we often need to write observing proposals. So many of the most cutting edge telescopes that astronomers use, such as the Hubble Space Telescope or the new James Webb Space Telescope, or JWST, which was launched last year. So these major flagship instruments have a competitive observing proposals process where any astronomer, or anyone really for that matter, can write a proposal specifying the amount of time they would like on the telescope and what they would like to observe and what their scientific goals are and what their technical justifications are. And they can propose to NASA or whatever agency that runs these major flagship missions. And, they can submit their proposal and see if they're selected to be able to make these observations. So there are a lot of different hats that we have to wear, but that makes life all the more interesting.
Absolutely. I remember you for our listeners, Kenneth and I were always chatting, and he's always telling me about how he's traveling here and traveling there. He's got to travel a lot. I mean, obviously things ebb and flow, but I'm curious, Kenneth, like, what are you traveling for? And like, how often do you get to travel? Like, where do you go? Like, I'm very curious.
Yes. So yeah, that's definitely one important aspect of being an astronomer is you should want to travel because our ground telescopes on Earth are based in some of the most exotic, beautiful, and remote locations on Earth. And as an instrumentalist, we often need to go to these places in order to either install our instruments or decommission old ones or upgrade existing instrumentation. So these are all opportunities to go and check out these remote observatory sites. So some of these places are like on the Big Island of Hawaii, or in the Chilean highlands, in the Atacama Desert in Chile, or even on the Canary Islands and in the South Pole. There are all sorts of telescopes in these different locations, and there are opportunities to go and travel to these places to carry out our scientific mission. So traveling to observe is definitely a large component of what we do as instrumentalists. Less so as observers, though, because nowadays a lot of the telescopes that we use are roboticized, and so we're able to remotely control the telescope from the comfort of our own home, which is very nice at times, and allows us to get sleep instead of staying up all night. So actually, interestingly, very few astronomers need to stay up all night to observe anymore, because a lot of these observations are taken remotely, and you're sitting time zones away, and all you need is communication with a technician on the site, and you don't need to be there. So in modern astronomy, a lot of this is indeed becoming an automated process. But for us who do instrumentation, we have the privilege of actually going to these places and checking them out. And of course, like every other scientist, we have many symposiums and conferences that we go to, and these can be anywhere around the world.
That's super cool. I mean, I think dark skies, just in general, are some of the most beautiful things. This is personal, but I think they're beautiful. And I was hoping you were going to bring up the Webb telescope, because I was going to ask you about it. And, I'd like to hear your perspective as someone whose area of expertise is like the instruments and the components of, I guess, the tools and the telescopes and the technology is, I guess, twofold. The first aspect being, where do you think the future of that is going? Like, what's our next step after Webb? And then I think the other element is, how can, the general public utilize Webb, if there's a way? What message would you like them to take away from it? Because I think even just looking at some of the pictures, it's so inspiring, the clarity of the images. And, I think it's definitely influencing a lot of people and young people too, and piquing their interest in astronomy. So I'd like to hear your thoughts on all of that.
Yeah, that's a very timely question. So the JWST, to give everyone some background, is an infrared observatory that launched last year on Christmas. And it is a space observatory, and it actually does not orbit in the same way as Hubble. It actually orbits further than the moon, 1,000,000 miles to midnight.
Wow.
Farther than the Earth. So it actually sits at we call them one of the Lagrangian points. So it is it's called an unstable equilibrium. So it sits a little bit further from the moon in this spot, and so it has to actually have thrusters that corrects its position every so often. So we call it basically the Sun-Earth L2 orbit. And the reason for putting this telescope in that particular location, 1.5 million kilometers from Earth, is because it is an infrared instrument, as I mentioned. So you would see that it has a large honeycomb-shaped mirror, and it is coated with a very thin layer of gold. And the reason is because it needs to observe infrared light. And Earth is a huge radiator of infrared light. So in order for such a telescope to be effective, you need to have the mirrors pointed away from the Earth. So the mirror segment in totality is 6.5 meters in diameter.
Wow.
And so it's a large mirror, and underneath the mirror there has to be a sun shield in order to prevent any additional heat from creeping up anywhere close to where the mirrors are and where the detectors sit behind the mirror. So this is a major undertaking that has been in the works for the past few decades, and has finally, with cost overruns and delays, finally has made it up into the sky. And so one question you might be wondering is, why is the infrared so interesting? Well, there are many answers I could give, but one that I'm particularly passionate about is what we call dusty star-forming galaxies. And so in the history of the universe, star formation has not been a constant. Star formation now is actually less than what it was many billions of years ago. And about maybe more than 10 billion years ago, and that was actually a picture of the pillars of creation, I think.
Sorry.
For our listeners, Sarah just showed Kenneth a picture on Instagram of the pillars of creation, which is, correct me if I'm wrong, it's a nebula in just somewhere in space.
So the pillars of creation, if you look at them, is essentially a stellar nursery where you can witness star formation happening. So that is where new stars are being born.
Cool.
So if you extrapolate star formation throughout the history of the universe, and we have ways of doing this, right? So we have tried and true ways of estimating how much star formation there is today versus how much star formation there was 1 billion years ago, 2 billion years ago, 10 billion years ago. And so based on our findings, we find that around maybe 10 to 11 billion years ago, star formation was much higher than it is now. And one of the questions that we want to ask is, why is that the case? And James Webb Space Telescope is going to be able to answer such questions, because the infrared capabilities allows us to peer into high redshift regimes, which means we're able to stare further into the history of the universe than we ever have been able to in the past. So how does that work? So when the universe expands, the light is basically an electromagnetic wave. And when the universe expands, this electromagnetic wave expands with the universe, because space itself is expanding. And so you stretch out these waves. And if you stretch out these waves, what you're doing is making the wavelengths longer. The frequencies is actually decreasing, right? So if you decrease the frequency or increase the wavelength, what you're doing in effect is changing the color of that light. So the wavelength of the light determines what you see as its color, and if you change that wavelength, you're changing its color. So by increasing the wavelength, you're making the light redder. And so at some point, you're gonna stretch out that wavelength so much that it's not only just going to be red, it's going to be beyond red. And what's beyond the visible color spectrum, it's going to be entering the infrared. So a lot of the light emitted from the early universe 10 billion years ago is actually reaching us here on Earth now as infrared light. And so JWST is built exactly for the purpose of capturing this early light. And this early light is where a lot of these dusty star-forming galaxies were forming and creating new stars in the early universe. And in order to find out how galaxies have formed, how galaxies have evolved over the many billions of years of cosmic time, JWST is our time machine, our window to the history of the universe, to see how these galaxies have come to be, and essentially how we came to be.
That's absolutely incredible. Wow. It really is a time machine, isn't it? That's so cool. And just because it takes so long for all that light to get to us, wow. Yeah, I'm still processing the magnitude of a lot of these questions that physicists get to ask. And honestly, I'm really, really excited to see where this all goes. And I'm sure we're going to learn so many new things about the universe that we probably didn't even think of before, through a lot of these cool advances in instrumentation and advances in theory, all of these different kinds of things. And I really want to thank you so much for sharing all of this with us and our listeners. I'm sure, obviously, I feel like I have so many questions about this. I could talk forever about this. I'm so curious. But yeah, it's been incredible to have you on here, and thank you so much. I don't know. One other thing I'd like to point out to our listeners, kind of just a reminder that Kenneth has exemplified to us a lot of the important things about being a good scientist: being skeptical, being curious, asking new questions, being creative, all of these things. And so I think those are really important principles that we can take away from this. But yeah, I guess without further ado, thank you so much, Kenneth. It's been wonderful.
Yeah, it's been a pleasure. Thank you for having me. And I'm happy to, of course, keep answering any questions that anyone might have. And Anyone is free to reach out to me if they have further questions.
All right, and if you're interested in following along with the Interactome, you can find us on Twitter at the Interactome, on Instagram at Interactome_media, or on Mastodon at the Interactome at universidon.com.
Thank you very much for listening to us. Feel free to comment on posts, ask us questions there, or you can also just email us directly at interactomedia@gmail.com. Thank you very much, and we're looking forward to having you join us next time on The Interactome.